Welcome to the talk Learning from Evolving Data Streams. My name is Jacob Montiel. I'm a researcher at the University of Waikato in New Zealand. I would like to start with describing what is the standard machine learning. This is basically based on data batches, and that's why we also know it as batch learning. And it's describing this pipeline. So what we are going to do is that we're going to collect data over time, and it's going to be stored in some device. And then we're going to use that data to train a mathematical model that eventually will be deployed and will be used to get predictions on some unknown new data. This approach is the state-of-the-art performance for multiple applications. However, there are some situations where this might be challenging to take into real-life applications. For example, let's consider if our data is continually being generated, meaning that it's not available at once, as it is in many cases, where we have real-time data. And another challenging situation can be if data changes over time. So to exemplify this, we have this article from the MIT Technology Review related to the supply chain. And this quote explains what is happening. So it took less than a week at the end of February for the top 10 Amazon search terms in multiple countries to fill up with products related to COVID-19. So what happened here is that first, data was coming continuously, being generated by the users, and data was changing because the consumers changed their behavior. And what we saw is that automatic systems in supply chain were not able to cope with this situation, which resulted in some disruption. So this is the kind of situations that we are interested in dealing with. For this, we have an alternative, which is known as the stream learning. In stream learning, we are going to assume that data is going to be infinite. And in this situation, we have to maintain models in an online fashion. What that implies is that we have to work with unbounded training sets. We are going to incorporate data on the fly. We have to be resource-wise efficient because we are talking about infinite amount of data. And we need to detect changes and adapt to them. So when we talk about stream learning, we usually work based on these requirements. First, we are going to process one sample at a time, and we are going to inspect it only once. This is because it's unfeasible to store a large amount of data, and maybe you don't need to do it. Second, you are going to use a limited amount of memory for the same reason, because our data streams is going to be infinite. Next, we are going to work in a limited amount of time. This is because we have to be ready to read as soon as new data is being generated. Otherwise, we are going to risk to miss some of the data that is coming. And the fourth requirement is that we are going to be always ready to predict. This is a major difference with respect to the batch learning setting. Where does that coming from is if we visualize the pipeline of learning from data streams. So what happens is that our model is always going to be ready to get some data from the stream. So what happens is that it's going to take labeled data and it's going to use it to train or update it itself, its internal state, and then it's going to ask for more data. Now, it's going to use unlabeled data to get some predictions, and it's going to return those predictions, and then it's going to get back to this state where it's basically observing more information. So remember, we have to work with one sample at a time. There are limited resources, and we want to predict at any time. So to just exemplify how we do this, I want to take this example, the decision tree classifier, which is a very popular batch method, which has a very good performance. And the nice thing is that it has interpretability. So in this case, I'm showing a decision tree for deciding if you want to buy a new car. So what happens is that there are some features or some attributes that are important for this decision. Let's say that the first one is that for most users, they want to decide if they can do a test drive. If they cannot do it, then they are going to skip, or they are not going to buy that car. If they can't do it, maybe they're not going to decide if they based on the mileage or also in the years. So what we see is that we're going to have at the split nodes or internal nodes some features, and then in the leaves are going to take the decisions. Now, in this scenario, the construction of the tree is using recursive induction. So what happens is that we are going to take all the data and we are going to filter the data into the structure of the tree. We are going to decide what is the most important attribute. We're going to create the splits, and we are going to create this tree. Now, the limitation on this is that, or the trick is that we have to see all the data. And for doing that in stream learning, it's not possible. We don't have all the data. We only have one sample at a time. So how would we deal with that? There is the alternative, which is called the very fast decision tree, and also known as the Hovden tree. And the idea behind this is that we want to incrementally expand or split the nodes. And this is basically, we are going to start with a root node, and we are going to start collecting some data here. And at some given time, we are going to break it and split it. So we are going to have now two leaf nodes and one split node. And what was observed is that for doing this, we only need a small sample of data, and we don't need to see all of the information. And the trick of this is that we have to choose when I have seen enough information or when I have seen enough data to make the right decision on the split. And for that, it was found that the Hovden bound would let us to the correct sample size for doing that. So what is happening is basically that the Hovden bound is going to let us know when we should do the expansion. It is going to let us give us some theoretical guarantees that now I have seen enough data and I can do the split. So this split is going to keep going as we are observing more data. I'm just going to keep creating the tree, and then this is going to be happening incrementally as I'm seeing more samples. Now, this is a popular stream method that keeps some of the characteristics of the batch version, which is it has low variance, it has low overfitting, and the nice thing is that it's asymptotically close to the batch model. If the number of data is large enough, then the model is going to be very close, which is the case for the stream learning, that we are going to see large amounts of data. The other thing that is challenging is we were talking about changes in data. So in dynamic and non-stationary environments, the data distributions can change over time. So we have something called change detection. And the goal is that we want to raise an alarm if there is going to be a distribution change. One of the applications for this kind of drift detection is to detect changes in model performance. Here I'm showing some of the most common drifts that we see in applications. First, we have some abrupt change. So basically we are changing from one concept to the other. Incremental, when we have some intermediary concepts while we transition from one concept to the other. Then we have gradual change where the two concepts are going to be interacting during some transition part. Recurring, when we are changing from one concept and back. And what is important here is that in change detection, we are also going to be trying to avoid marking outliers as change. One popular method for doing this change detection is called ADWIN, which stands for adaptive windowing. And what it's doing is that it's going to keep an adaptive window with two sub-windows. So what ADWIN is doing is that it's going to keep two sub-windows. It's going to decide based on the data that it has observed, where is the point that is going to keep the average of the two sub-windows similar. And what happens is that as we observe more data, it's going to happen that at some point the averages are going to be different. And if that happens, that means that the distribution is changing, and then it's going to raise an alarm. Now, the nice thing about this is that this adaptive process is also maintaining the sub-windows in a online manner. So it provides logarithmic memory and update times. So this is very useful for stream learning applications because it's basically keeping the amount of memory used for monitoring the stream under some constant memory, and the processing time is also sublinear. So in this example, I'm showing why we want to use in some case scenarios stream learning methods. In this case, this is a synthetic data set with 3 abrupt drifts. And I'm comparing two popular algorithms. At the top, it's a batch model, which is XGBoost, which is an ensemble method that is a collection of trees. And in the bottom is the stream learning method called adaptive random forest, which is a stream learning version of random forest, which is also an ensemble method for trees. And what happened here is that in the case of the batch model, this was trained on some data beforehand to just be employed in this stream. So what happens here is that we see that, okay, the concept is the same to what I've seen to train, and XGBoost is doing fine. But then what happens is that after the first drift happens, the performance drops because the model that was trained doesn't recognize this data, so it starts to phase. Then we see another drift, and actually it goes up because maybe this drift, this new concept is kind of similar to what it was before, and then it kind of improves. But then we see another drift, and this new drift or this new concept is not as close as the previous one, so we see that performance is not as good as it could be. On the other hand, we see the stream model that at the beginning we see that it starts learning, and then it keeps a good performance. Then it sees the first drift, it drops, but it recovers quickly. That's the most important thing, that we can recover quickly and get good performance again. Another drift happens, and we see the same thing or the same behavior. So in this case, the adaptability and the reaction time are very important. And what is usually the case in some deploy models in the batch learning model is that when they see a drift or there is a drop of performance, this is basically where people start panicking and people start trying to see what's happening with the model. We have to trigger again a batch learning pipeline, and it gets additional steps to make these batch models work in the context of changes of data distribution. Now, I have been talking about evaluating models. And this is an important thing because also in the scenario of stream learning, there are some considerations that we need to take into account. So for doing evaluation of stream learning methods, we have two main approaches. One is the holdout approach that is similar to the case of the one in batch learning. And we are going to keep an independent test set, and we are going to store some of the data from the stream there, and we are going to use that test set to test our models at some intervals. On the other hand, a very popular approach in stream learning is the frequential evaluation, also known as test and train, because here the order matters. So the nice thing about the frequential is that we are going to use all of the data from the stream. Why I say the order matters is because we are going to take one sample, we are going to use it for testing, and then we are going to use it for training. And again, the nice thing about this is that we are going to use all of the data from the stream. Another important thing is, how can I do this? And for that, let me introduce you to scikit-multiflow, a machine learning package for data streams in Python. The objective of scikit-multiflow is that it is easy to design and run experiments, and it is easy to extend existing methods. Scikit-multiflow is designed for users with any experience level. It has a low learning curve and works with Jupyter notebooks. The current state, it contains multiple features such as data generators, stream learning methods, change detector, evaluators, and more. And now I would like to give a short demo on how you can use scikit-multiflow. We're going to run a classification task. We're going to show how to implement the frequential evaluation, and then we're going to show how you can use the evaluate frequential class in scikit-multiflow. The second part is about concept drift detection with the detection test, and then we're going to evaluate predicted performance when there is drift in the data. So for the first part, we are going to run a classification task. Here I'm going to use as a stream the C generator. This is a generator that is going to be creating data on the go. And then we are going to use as a classifier the naive Bayes classifier. For the frequential evaluation, it's actually very easy to implement as a loop. In this case, we see that the frequential evaluation is going to first work until I have reached the max number of samples. In this case, I'm setting it to 2000. And the other condition is that there must be data in the stream. So in this loop, what we are going to do first is we are going to query the stream for data. By default, we are going to get one sample, and then we're going to store features and target for that sample. Next, we are going to predict. Remember, the frequential evaluation, first we're going to test. So we are going to predict on these features, and we're going to get some prediction or some class predicted for this by this classifier. In this case, I'm just going to check for accuracy. So I'm going to compare what I predicted or what the model predicted versus what is the correct answer from the stream. And then we are going to proceed to incrementally training the model with the new data. So in this case, we're going to call partial fit, and I'm going to pass the features and the class target. And we are going to keep going this until we have reached the conditions marked by our loop. If we run it, we see that the 2000 samples were processed and the accuracy is above 93%. And the important thing here to remember is that we are training and testing on one sample at a time. Now, for making our lives easier, scikit-multiflow implements the frequential evaluation in a class that also has some additional functionality. For this example, I'm going to train two models. I'm going to use the naive Bayes and the SVM from scikit-learn. This is just to show that we have compatibility with incremental models from scikit-learn. But it's important to mention that scikit-learn is focused on batch learning, and it only has some limited number of incremental methods. In this case, then I'm going to set up my two estimators and again the same stream. And I'm going to set up my evaluation. And here I'm going to ask for a plot, just defining the number of samples that I want to use, and the metrics that I'm interested in monitoring. In this case, it's accuracy, the kappa statistics, running time, and model size. And if I run the evaluation, then I'm going to get a dynamic plot. What we are seeing here is the evaluation over time. We see that SVM starts performing a little bit lower than the NVM, than the naive Bayes. But then it performs better in the last part of the stream, and it provides a better performance on the long run. We see here that we are also getting the training time, prediction time, the memory of those models, and we are evaluating for the current state, meaning this is the evaluation on the last n samples that are in a sliding window, and the mean performance, it is basically the performance over all of the stream. Scikit-multiflow is also going to give you a summary at the end of the evaluation with all that information. In the second part, we're going to check a test on concept drift. So for this, we are going to generate a synthetic data that is going to be composed by three different distributions. So here we can see that in the first 1,000 samples, we have a distribution, then we have another distribution, and the last part of 3,000 of the last 1,000 sample is the other distribution that we're going to use. So for this test, what we're going to do is that we are going to use ADWIN to detect changes, and what we want to see is changes here in 1,000 sample and after 2,000 samples. So for this, if I initialize ADWIN, we can run this in a loop. So here is a for loop where we are going to pass one single sample from the stream. We are going to pass it to ADWIN. And after we pass one sample, we are going to query ADWIN to see if it has a drift has happened. It's important to see that we don't have visibility of all the data. ADWIN only sees the current sample that is being passed at a given moment. So if we run it, then ADWIN is saying that there was a change after sample 1,000 and there was another change after sample 2,000. Now, this is important because in many applications, drift can impact the predictive performance of our methods. So for showing this, I'm going to run a comparison between the stream learning methods. One is the Hovding tree, and the other one is the Hovding adaptive tree, which is an improvement over the original Hovding tree, and it uses ADWIN at the nodes to detect changes. If it sees that there is a node that its behavior is changing or performance is changing, then what it does is creates an alternate branch, and eventually it will be replacing the original branch if it performs better. For this test, I'm going to load a stream from a file just for experimentation, and this data is from the gradual generator. It has 3 gradual drifts at the 5,000, 10,000, and 50,000 samples. This is just also to show that you can load data from CSV files in scikit-multiflow. I'm going again to initialize my Hovding tree classifier and my Hovding adaptive tree classifier, and I'm going to use the valid frequential class to perform this to benchmark these two methods. So here we see how the two methods are performing. They have a very similar performance at the beginning because basically the Hovding adaptive tree works as the Hovding tree when there is no change. But what is interesting is after the first change, we see that the Hovding adaptive tree is better at recovering than the normal Hovding tree. The same happened here at the one after 10,000 samples. We see that Hovding adaptive tree recovers faster, and that in the overall performance leads to better numbers, which is what we want to see. And we want to keep this performance as high as possible. Also interesting to see is that the memory of the Hovding adaptive tree is smaller. This is showing that the model is actually changing internally. So when it's detecting changes, it's changing the structure of the tree internally, it's replacing the branches, and that's why in the end we have a better performing method that is also smaller in memory. scikit-multiflow is an open source project and it's available in GitHub. It's also being distributed by other means such as pip and conda. There is also a Docker image that you can use. scikit-multiflow works on Linux, macOS, and Windows. Also, it's an open source project. We are always welcoming contributions. If you are interested, you can look into the repository in GitHub, and also you can reach us in our GitHub channel. We have a pool of projects in different areas, but are also open to hear your own project and ideas to see how we can collaborate. There are two main takeaways from this talk. First, stream learning is an alternative to standard batch learning. especially if data is continuously being generated and if data is non-stationary, so it evolves. Remember concept drift. The second is scikit-multiflow, a machine learning for data streams in Python. The two nice features about scikit-multiflow is that it's easy to design and run experiments, and it's also easy to extend. I would like to thank you for attending this talk, and also I would like to thank the organizers of the conference and all the anonymous reviewers that participated.